You ready? I'm going to go ahead and start. It says 9:05 out there. Okay. So this is just a review of where we were. We talked about preheat yesterday, and you want to be at least above 50 degrees Fahrenheit before you start to weld on steel, just to remove the layer of moisture that you can't see. But as you know, if you get down to frost temperatures, you'll see the ice form on something and it turns white. But even before, at 33 degrees, there's actually a layer of moisture that condensed that you might even be able to feel it at 33 with your finger, but you can't see it because it's water, it's transparent. But once it freezes, you can see the frost. Well, there is a layer of moisture even at 40 degrees, and it's more moisture than you really should be welding through. Between 100 and 300 degrees F, typically, we're just trying to slow down the cooling and keep the thing in this 100 to 300 degree range, because we know that'll accelerate the evolution, the bubbles of hydrogen coming out of the surface. And I showed you the glycerin example of stuff. And you just speed that up, it allows the hydrogen to escape. So in the first one, if you take this Venn diagram, and I don't know if you've noticed, I've been doing them consistently. Stress, hardness, and hydrogen content. Other people might put them in a different, but for this class I've been keeping stress at the top, microstructure, and hydrogen content in that order. So what we're doing on the first one, we're removing hydrogen. On the second one, we're removing hydrogen, trying to shrink that circle, right? The third one, if you're above 300 degrees, you get tempering, and you reduce that, and tempering will reduce the hardness, and you're also trying to let the hydrogen escape even faster. But the real thing is you're trying to temper, so you're reducing hardness by tempering, you're also getting rid of hydrogen more quickly. So you're actually reducing two circles. You haven't changed the residual stresses, okay, so far as that goes. And in fact, this is a tempering curve I showed you before, that basically, if you take a piece of steel and you quench it to its maximal hardness for a 1021 steel, the maximal hardness, which is a function of carbon content, may be Rockwell C 37 or 38. You get above 150 C, 300 degrees F, and the thing will start to soften by tempering. And you temper between 300 degrees and 600 degrees Fahrenheit. You avoid 600 to 1,000 because you get something called temper brittleness in steels, which this is not a metallurgy of steels. This is supposed to be a welding course. But eventually, we're going to see that we do post-weld heat treatment up here in the 1100 to 1200 degree range. And in fact, I might as well do it. Here it is up here on the board. Post-weld heat treatment is another process that we might do for difficult to weld steels, where we heat them in the 1100 to 1200 degree Fahrenheit range, typically for 1 hour per inch of thickness. And that 1 hour per inch of thickness is, you can measure the temperature on the surface. You put it in some furnace, and when the surface gets up to 1100 degrees, you then now need to soak it so the temperature on the inside gets there. I mean, if I put a roast beef in the oven, I might get it done on the outside, but the inside's still rare, okay? So you need about 1 inch per inch of thickness in order, with the thermal conductivity of steel, to allow it to heat up in the center. I want medium roast beef. I don't want rare roast beef. So the problem here is, for something between 1 and 3 inches, an hour per inch of thickness is about right. You start going to 10 or 12 inch thick steel, and it turns out you can sort of get away with a half hour per inch of thickness. Nowadays, they have little computer programs that will tell you exactly how long it takes to get the inside up to a reasonable temperature. But in the old days, one rule of thumb you'll often hear is 1 hour per inch of thickness. But that only applies in the couple of inches thickness range. Above that, you actually can do it a little quicker. You temper to lower the hardness. What this does at this temperature, you're tempering to lower the hardness, which means I'm really lowering the hardness. I mean, this stuff is, you're not losing the martensitic structure, but you're getting to be relatively soft compared to the maximum hardness. And that's going to be good in terms of lowering the hardness circle, okay? You're also relieving the residual stresses. The material at 1100 to 1200 degrees, this is called stress relief heat treatment. And the locked-in stresses, there's enough creep at the steel. The steel actually loses about half of its yield strength when you get to 1100, 1200 degrees. And that means the steel can actually start to deform and relieve those locked-in stresses. So a piece of steel that if you quenched it and cut off the top layer, it might bow up because you took off the tensile or compressive surface layer. If you put it in 1100 to 1200 degrees and then machine it, it will stay flat. Okay, it's been stress relieved. And you're also removing hydrogen big time because you go to 1200 degrees, the hydrogen is going to go out there very rapidly. And so what you've done with the post-weld heat treatment is you've reduced all three circles. I tried to dash in the original circles. So you get no overlap zone. And remember, it's the overlap zone, which is what causes, is where you have the danger of cracking. You will get cracking in theory, the way we've kind of done our little diagram. So those are the reasons for preheat and post-weld heat treatment. Now let me tell you, post-weld heat treatment is not cheap. Post-weld heat treatment will cost as much usually as welding the part to begin with. Post-weld heat treatment isn't hard. If you've got a part the size of this table and you've got a furnace bigger than the table, you just stick it in the furnace. In air. You might get a little oxidation, but you can clean that off with a sander, or you can peen the surface and knock the scale off, or whatever. You can actually paint over it if you want in some cases. It's not a thick oxide. It's not a terribly thick oxide. It's a black oxide. It's fairly adherent. Or it's a, what we call black iron pipe, and I think I've explained that before to people. In any case. So stress relieving is not too bad on something the size of a table, but what about a pressure vessel the size of this room? It's a bit of a problem. Unless you have a furnace that big, and some of the pressure vessel shops do. I mean, there are heat treatment furnaces at a pressure vessel shop that could be 20 foot square by 30 feet long. In fact, I printed it out, but I forgot to get it off the printer. If you go to Cooper Heat is now purchased by someone else, but they, for many years, were the big company around the world doing on-site heat treatment. So they had a picture that I forgot to bring of a 118 foot long pressure vessel that will be stood up in part of an oil refinery. You can sort of tell all the nozzles and stuff coming off of it. Probably 3 or 4 inch thick steel, probably going to have 100 atmospheres type of gas in it at 1100 degrees or something, whatever. But it's thick enough wall, it's all welded construction. You're going to have all kinds of residual stresses there. And if you don't do something about the residual stresses, you'll have problems. You can have fatigue problems because if you have residual stresses, the fatigue's already got a head start. You might apply some other stress in service, but you've already kind of given it a head start with potential residual stresses in some locations. So I can tell you some stories about some of those things in a little bit. But Cooper Heat will come to your site for a fee. It'd be a pretty good fee. And they will build a furnace around your part. And so it can be in the 118 foot long one, they actually had some little kind of railroad tracks, and they had a box furnace that was 118 feet long, full of insulation around it. Other cases, they may do a local stress relief. You have a nozzle and a pipe coming off a big pressure vessel, and you just have to do the nozzle. Well, they actually have heating blankets, which are just little ceramic pieces with wires in them, and bigger than a welding power supply. Pump a couple of thousand amps through that resistance heater and heat the whole thing up locally. Put a bunch of refractory blankets around it and locally heat treat it. There are all kinds of rules on local heat treatment, because if you do local heat treatment somewhere, you're going to get into this intermediate range where you get temper brittleness, okay? you don't like to be in the 600 to 600 to 1,000 degree tempering range. Between here and here, you're going to be here. If you're doing local heat treatment, obviously something's cold back here, something is in the intermediate range, and you could damage your steel, depending on the type of steel, by doing local stress relief. So sometimes you have to stress relieve the whole vessel. And in fact, there is really no pressure vessel so large that it can't be put in a furnace for stress relief. There are some vessels that are so large that we can't afford to do it. And one pressure vessel that is so large that we can't do a thermal stress relief is called a submarine. Okay? Now we're talking 300-400 feet long, 30 feet in diameter, and even if you could have a vessel that big, it's already got a few other things inside that don't want to go to 1,100-1,200 degrees, or you're going to destroy the insides of the ship. Okay? So you can't really put it in a furnace. Yes?
Can't you still heat treat the weld?
You can locally. That's local stress relief, and you have to worry about what you're doing to everything else.
Wouldn't that be more important to do the weld since it's trying to be smart structure?
Yes, but the problem with like the submarine steel is you've already heat treated it to get a maximum strength, and you want that strength. A pressure vessel, very rarely, I'm not saying we don't use quench and tempered steels for pressure vessels, we do, but in a nuclear submarine, you're basically using all that strength for the strength of the vessel to be able to dive. So they don't use thermal stress relief. They do stress relieve the welds, but they don't do it with thermal energy. You have to go to another type of energy. What type of energy would you use? Mechanical. The first deep dive, okay, the first time you dive in that submarine and go a little extra deep, okay, deeper than you want the regular officers in the Navy to take it, but you're going to do a proof load test, and you're going to take it down deep enough that you will mechanically relieve the residual stresses, okay? So you relieve the residual stresses. It's not that we don't stress relieve the hull, but we don't do it at temperature. We do it mechanically. We do it by taking it down very low in the ocean, okay? I can't tell you how low because I can't. That would give you some idea of what the maximum depth capability is, which is classified, okay? It's classified because then they know how deep to set their depth charges, okay, and things like that, okay? There are reasons for this. It's actually more operational. You can't go maximum speed at maximum depth because if anything goes wrong and you all of a sudden start going down, you can get a little too deep too quick. So your maximum speed in a submarine is at some intermediate depth or above. The maximum depths, you have to go a little slower, be a little more careful because you're walking along the edge, okay, of this thing. But anyway, so we stress relieve. But the best quality control, one of the best quality control techniques I know they use on Navy subs, and that is the top management of the shipyard has to go on that first deep dive. They may not have made the welds, but they're responsible for it. And yes, some top Navy people also have to go. So you invite some VIPs to your first deep dive. And this is a very good way of ensuring quality control in the shipyard. Okay, you put the rubber, this is where the rubber meets the road in terms of quality control. When the top management gets paid the big bucks, gets to put their life on the line for the quality of the product they just sold you. Okay, just a thought. Okay, I think it's a great way to do it. So, and obviously the Navy thinks it's a good way too. I don't know what the management of the shipyard thinks, but actually I tell you the things. They want to make sure that's a very good weld that they made on those hulls. Okay. Okay. I told you I'd tell you some stories of examples where someone may have done something, may not have done something. One example, and I'm doing this to a certain extent because some people yesterday said they like the stories. Okay. You have to remember the stories are good and they help you remember long term, but they don't necessarily help you. It's not as dense in information transfer, but it actually sometimes has other information that goes along with it. So one type of question is, when do you post-weld heat treatment? When do you have high enough residual stresses, this part right here, that circle gets big enough? And I think I mentioned to you that somewhere around an inch or 2 inches thick, you can have yield level residual stresses. In fact, in the boiler and pressure vessel code, which is the ASME code for building pressure vessels, they do not require stress relief below 1.5 inches thick, except for certain types of weld geometries like a fillet weld at 1.25 inches. I may be getting some of this backwards. But anyway, some welds at 1.25 inches, you don't have to stress relieve. Some welds at 1.25 inches you do. At 1.5 inches, you pretty much always have to stress relieve. Okay, so it depends on the geometry as well. And they have these rules. It's UCS 56, I think is the table. UCS means unfired carbon steel. 56 is the table in that section for how to weld or how to design unfired pressure vessels in carbon steel. So what's the story on that? Well, the story on that is the Helms project in California. So the Helms, anybody from California? No, you're from California. So you've heard of the Sierra Nevada mountains. Okay. So Pacific Gas and Electric, you've heard of them. Okay, big utility out on the West Coast. So Pacific Gas and Electric, around late 80s, 90s, decides they have all these nuclear plants they built on earthquake fault zones and things like that, just for safety reasons. They're actually shutting some of those down now, but nonetheless, they decided they need something to store the energy because a nuclear reactor likes to produce energy 24 hours a day at a certain level. It doesn't like to be started up and slowed down. It likes to just slow and steady wins the race. This is the tortoise and the hare type of story. Nuclear reactors are the tortoise that just keeps on plugging along. But people, they like to come home at 5 or 6 o'clock, start fixing dinner, turn the air conditioner on. And so there's a peak in usage around 5 o'clock. There's a peak in the morning before they go to work. In any case, usage of electricity is not uniform, and so they like to level that out so the nuclear reactors can work the way they like to work. So they decide to build a pumped water storage project. We have pumped water storage projects in western Massachusetts. Any place you got a hill and water coming down, you could build a pumped water storage project. And all it is, and they've been building these in California for 100 years, okay? They call them penstocks. Anybody heard of a penstock before? Yeah, what's a penstock?
Well, I've heard of these pump water storage things before.
Okay. A penstock's just a pipe coming down the side of the mountain. So if I've got a hydroelectric plant, I got water up here, I got turbines down here, and I have to connect them, I connect them with a pipe, and that pipe is called a penstock. Okay? Some of these are pretty big. In this case, we had a lake that had already existed in the Sierra Mountains at about 8,000 or 9,000 feet. Had another lake at about 6,000 feet. And they needed to build a penstock between the two of them. For the energy requirements and the size of the lakes, they decided this should be a 22-foot diameter pipe. Okay? This is a pretty good sized penstock. And anyway, 22-foot diameter pipe and 188 psi of water. Actually, it's 188 psi at about 7,000 feet, because most of this penstock, they just blasted a tunnel right out of the rock and then lined it with steel and concrete and built this thing, and now it's supported. You don't have to have lots of structural support for it. But there was this one canyon that they had to cross, and as I remember, it was about 300 feet, or no, it was less than that. 20 plus 160 feet, something like that. So they had to cross this canyon. Nature didn't give them rock there to just tunnel through. So they came out of one tunnel, crossed the canyon into another tunnel, and they had to build a 22-foot diameter pressure vessel that would not be supported anywhere else. Well, it's convenient. Somewhere in the middle here, they could put a manhole at the bottom of this 22-foot diameter pipe, so whenever it was drained, they could take the manhole cover off, put a ladder up there, and somebody could crawl up in there and walk around in this dark tunnel. What fun, right? Well, so they were welding this 20-foot diameter pipe up in the mountains. You don't just kind of put that on a truck and carry it up to the mountains because the roads aren't there, okay? You got to build it on site. Field fabricated, 22-foot diameter pipe. This particular 22-foot diameter pipe section with the manway, the reason I remember it was about 160 feet or 140 feet or something across the canyon. Some of them were 40-foot long sections. As I remember, there were 3 of those with a 20-foot long section in between. So here we have Granite Mountain, Granite Mountain. There's, on the bottom of this, there's a little manway. Okay? Little manhole so someone can crawl up in there down at about the 6 o'clock position. So they built this thing, and they had to build it on site. They roll the plates down in Fresno, some big shop. They take the sections of rolled curved plate up here. They'd set up something. They'd start welding them together. Okay. Now the easiest weld something like that together is to do vertical welds, or what will become your longitudinal weld. So you stand up the plates, several of them, weld them together, so far as that goes. So they'd weld them together, and they cut a hole in here for the manway nozzle, and they were starting to weld it. It was getting to be winter. The snows had started in October. It was now mid-November, and they were going to shut the whole thing down just after Thanksgiving. They wanted to shut it down before Thanksgiving, but they were a little behind schedule. And they couldn't keep it going all winter because there would be 20 feet of snow there, by December. So they got the guys welding, 1.25 inch thick nozzle here, doing fillet welds on this thing. And so the fillet weld looks something like, if this is the flange, and this is the pipe coming down, I'm going to put a fillet weld in here. Okay? So they're making that fillet weld, and this is big enough. It's stick weld. It's in the field. Stick weld, so you got some hydrogen in your weld metal. It's a pressure vessel steel, but it's sort of a mild steel. It might be 0.3 carbon, a little higher towards a medium carbon. Needs some preheat. Okay? So they preheated it, but in fact, and this is actually the wrong weld, that was the flange. This is another weld up here where it goes to the top of the pipe. Okay? And they were welding in the overhead position, and we know they preheated it because we had pictures showing 3 feet of snow on top of this thing on the inside of this pipe, this laying horizontal. Okay? Well, it must have been preheated to 100 degrees because you had 3 feet of snow 1.25 inches away. Right. Okay? Well, the supervisors had told their families they were going to be home for Thanksgiving. So they left in mid-November and left the welders to do the work themselves. Okay, let the fox watch the hen house. Okay? So they didn't bother to shovel the snow off the inside. That was a lot of work. Sort of like we preheated it on Friday and we're welding on Monday, right? So they just welded this thing with snow on top of it, 1.25 inches away. I don't think they got very good preheat. Okay? And they're welding with stick electrodes. And who knows, maybe they're not even drying the stick electrodes. There's no supervisor around to check on them, right? They're just finishing up. And the sooner they can finish up, the better chance they get to be home for Thanksgiving, right? So it's not as if they're trying to do their best job or anyone's looking over their shoulder. So they weld this thing, and they let it, they get out of there before Thanksgiving. The whole thing gets frozen at about -20 for the rest of the season, okay, the winter season. They come up in the spring, the snows have started to melt. Around April, they mounted this thing across the canyon, and they load it up. 188 PSI. 20 hours later, There's some workmen there in the little canyon, and they have a little, porta potty. The guy's coming out of the porta potty, just finished his business. He's looking about 50 yards ahead of him at this crossing, and he hears kapow, crack, and he sees water streaming out of this thing, and he starts heading for high ground, and he makes it to high ground along with a couple of friends. But in the meantime, the whole thing blows apart, brittle fracture. Oh yeah, they were supposed to post-weld heat treat this, according to the code, but they didn't bother to, okay? So it had plenty of residual stresses. They hadn't done the post-weld heat treatment. It probably had plenty of hydrogen because they didn't preheat it properly. And it had a high hardness microstructure because they didn't preheat it properly. So they did about everything wrong you can imagine. And they knew that it had gotten to 188 psi and didn't crack for 20 hours. So that sort of, Tom Meeker says, hydrogen cracking, delayed cracking, hydrogen has to diffuse and get to its place. Even though it's 9 months later, this is the oldest hydrogen crack from time of welding, but you got to remember, they froze it for most of the winter at -20. The hydrogen can't get out. It doesn't do a lot of damage because it's stuck, but it can't get out either, okay? So as it warms up, and then you stress it, add the applied stresses, and wait 20 hours, I think it's 20 hours, okay, it might have been 8 hours, I don't remember exactly how long it was. But the thing blows apart. Well, they had a valve up at the top lake in order to shut it off, except the valve's a 22-foot diameter valve. And they didn't have anybody at the top lake to do that. So these guys go hustling up there in their pickup truck. They have these dirt roads. And they get there, and it's not a small valve. It takes a half an hour to close it, okay? In that half hour, the upper lake dropped 50% of its height, and the water's coming rushing down the canyon, into the canyon, coming out of this end at 188 psi, 22-foot diameter, 4 million horsepower, okay? Hits this granite wall, erodes it away 100 feet back. They just made a 140-foot canyon into a 240-foot canyon crossing, okay? In the meantime, the water has to go down the canyon, down through the woods, and end up where it's supposed to in the 6,000-foot lake, okay? Now, a few bears and raccoons and other people were very upset by this, okay? It disturbed their habitat quite a bit. It also built this beautiful sandbar beach for about 100 yards down at the lower lake, okay? So, but it's all about failure to preheat, failure to post-weld heat treat, and hydrogen and
What
brittle.
was the name of this company?
Pacific Gas and Electric, okay? Oh, actually, I'm sorry. Pacific Gas and Electric was the owner. The company that did it was American Bridge Division of U.S. Steel, okay? They're big contractors back in those days. Now, to tell you the rest of the story, I'm shortening it a little bit, but it went to trial in Fresno, California in the early 90s. Why did it go to trial? It was a $100 million loss on an $800 million project. Pacific Gas and Electric really didn't want to have to take it to trial, but they wanted to recover their money as a loss, and they went to the California Public Utilities Commission and said, we want our $100 million that it costs to repair this thing as part of our $800 million project, and we want to put it in the rate base, and this will raise everybody's electricity costs by so many tenths of a cent, okay, in this part of California. And the Public Utilities Commission said, if you say it was a defective weld, and if you don't take American Bridge to court to sue them and get your money back, we will not allow this $100 million in the rate base. Okay? Well, so here's a $100 million extortion that the Public Utilities Commission is giving to Pacific Gas and Electric would be delighted to just forget about the lawsuit and just put it in the rate base and just spread the peanut butter all over all the citizens of California, but the Public Utilities Commission is there to protect the citizens. So they go to trial, 6-week trial, I was the last witness. But in any case, we lose. PG&E doesn't really care. They had tried, and now they go back to the Public Utilities Commission and say, well, the jury decided it was a foundational problem. Our supports, our foundations to support the pipe were inadequate. They shifted, and it had nothing to do with hydrogen or the well. It's a long story about how American Bridge argued that. In my opinion, they were wrong, but some of our metallurgists, which were some of the highest paid metallurgists in the world at the time, were also wrong. In fact, at the time, I was charging like $150 an hour. This is like late 80s or something. And the top-notch metallurgists from this big multi-million-dollar consulting firm located at the time in Palo Alto, their experts were charging $275, almost double mine. And I used to go around saying, well, if you get $275 an hour for the wrong answer, what's the right answer worth? Right? Anyway, that's when I learned a lot from that 25 years ago about how to bill, okay? If you give someone the right answer, it's worth a lot of money. You give them the wrong answer, it's not worth a dime. So that's what John Wolfe used to say. John Wolfe was my thesis advisor. Anyway, I can tell you a story about John Wolfe. But anyway, we lost, and not only did we lose, this big shot metallurgist for this 1,000-person consulting firm had said 3 days after, in the second day of the inspection, 3 days after the failure, he had been there and he said something about it was American Bridge's fault. Not a good idea to start slandering them in the paper after only 72 hours. And so they not only didn't have to pay $100 million, they received $17 million in punitive damages for slander, okay? Because the metallurgist hired by PG&E to investigate it, that was on site, basically made a press announcement that he should not have made. So, okay. In the meantime, I firmly believe, and if anybody wants to, I guess I can spend that half an hour, not today. But let me tell you the John Wolfe story, because it's really a good story. I learned it, he told it to me as a freshman at 3091.
Do you remember the name of the lake? I'm just
Sorry,
trying to
what?
find the story. I'm trying to find
The lake?
Yeah.
Oh.
Yeah,
It's called the Helms Project, H-E-L-M-S, that's all I remember. Okay, I know I never knew the names of, I probably knew the names of the lake, but.
Okay.
It's a pumped water storage project, okay? If you look up pumped water storage, Helms Project, California, it might show up somewhere. Anyway, so the John Wolfe story about charging fees as a consultant this is one of my favorites. My favorite is actually Steinmetz. Has anyone heard the story of Steinmetz? Do anybody know who Steinmetz was? So Steinmetz was a great mathematician who basically learned how to use imaginary numbers to explain AC electricity. And he worked for General Electric or as a consultant. Brilliant man. And at one point, around 1900, Westinghouse or somebody put in this big generator, or General Electric had or something. They hired Steinmetz as a consultant. And for 2 days, he asked for a set of drawings and he asked for a chair. And he sat in front of this huge generator built around an electrical generator with the drawings, trying to understand why this thing was not, they just installed it and it wasn't working. And finally, on the second day, he asked for a piece of chalk. And on the second day, with the chalk, he draws a little box and puts an X in it. He says, cut the steel case open here, cut this connection in the copper windings of the generator, and seal it back up, and that will fix it. And they did, and it worked. And General Electric is very happy, and the people of New York now have electricity again. And Steinmetz sets a bill to General Electric for $1,000. Now in 1900 or 1910, whatever this was, $1,000 was a lot of money. And the chairman of General Motors supposedly writes back to Steinmetz. He says, "Well, we thank you for fixing the problem, but how can you justify a $1,000 bill?" And Steinmetz writes back, "Chalk, $1, knowing where to put the X, $999. Okay? So it's what you know that you're hiring when you get a consultant. So John Wolf, I don't know, late 40s, early 1950s, gets a call one morning. Boston Edison, who generates electricity, had just had overnight all the stainless steel in their electrical generating plant just fall apart by corrosion. And John Wolf gets a call and he says, I know what your problem is, but I won't tell you the answer unless you agree to a $5,000 fee. Well, $5,000 in 1950 or whatever was like 2 or 3 years salary for an engineer. It's a lot of money. And they kind of, well, if you're right, we'll pay it. And so it turns out John Wolf was an interesting old guy. He actually, when I was a freshman, he had the office that I'm in, and he was teaching 3091 for the first time, and I was taking it anyway. He was a crusty old German, okay? And in fact, during World War II, he knew there was something going on at MIT that involved uranium, okay? But he didn't know what it was because he was German, and they didn't let anybody of German or Japanese descent know anything about certain things, right? But John Wolf had been studying trace metals in different wars of the world, and he knew there's something interesting with a departmental cocktail party reception or something. One night he says, you know, there's a lot of uranium in the oil in the Balkans, okay? And the next morning he said there were 2 FBI agents in his office asking him what he knew about uranium, okay? So he was right, there was something about uranium going on, and part of the Manhattan Project was here. Morris Cohen and John Chipman were working on things. Anyway, get back to Boston Edison. So they agreed to the $5,000 fee if he's right, and John Wolf then tells him, he says, well, you just started bringing in oil from Venezuela. And they said, yes. This was the first shipment of oil. They just opened up the oil fields in Venezuela.